Hello, hello, welcome. We are going to go through the first investigation for mathematical methods stage one, and we're going to be looking at polynomials. So we've been working through polynomials in chapters 2 and 4. So chapter 2 had a lot of work on quadratics. In chapter 4, you've introduced cubics, and in this assignment, we're going to be working through order 4 and actually order 5, which is order 4 is commonly called quartics, and after that we just get sick of naming them, so we say order 5, 6, 7, 8, or degree 5, 6, 7, 8 is actually the term we've been using. So if you remember, let's go back and remind ourselves what we've been working on. So this is quartic polynomials. The basic function y equals x to the power 4 looks something like this. Like almost like a quadratic, but it's just wider. You notice how it hangs around the value of 0 more, and then it just rises very steeply. And there's a reason for that. It's basically you've got 4x's times together. So anything close to 0 becomes very close to 0. Anything away from that rises very fast. Or if you put a number in front, it would fall very fast. But the general function looks more like this. Ax squared, ax to the power 4 plus bx cubed plus cx squared plus dx plus e, where a, b, c, d, e are the constants. There's actually a lot of things that can happen with this. So basically, the larger you make your polynomial, the more freedom you have. And I've actually graphed some combinations. Basically, this is a summary of all the things it could do near the x-axis. We'll explain that in a minute. Because that actually comes up in the introduction as well. And some of my colleagues were a bit curious about how they come up with the number 7. Now, I actually have 8. I'll explain them each in order in a minute. But okay, so at this point you should have already done some of this content, but it's worthwhile revising this because you can actually go back. And when I taught this content, I talked about how the factors react. So a single factor, x minus alpha, cuts at alpha. A squared factor touches at alpha. We remember this from cubics as well and quadratics. A cube factor, the graph cuts at the x-axis and is flat at alpha, so it's like horizontal there, whereas that one kind of can go through at a different angle. A quadruple factor touches and is very flat, unlike that's not quite as flat if you look at those ones. And you also have some examples where you may have a part of the graph that does not cut. So you have like delta less than 0 for one of the quadratic factors and delta less than 0 for both of the factors. And I've actually summarized it all here, but let's have a quick look at the investigation. So let's start this. Okay, so in the investigation, you start talking about quartics. Okay, and obviously the leading term, the leading coefficient of x4 cannot be 0. Every real polynomial, so when we say real, it means that these numbers a, b, c, d, and e are not complex. It's not a concept you have discovered yet, unless you've done some other private study. But in terms of what we mean by real numbers, it means numbers that are included on your number line from minus infinity to positive infinity. And essentially, essentially the numbers you're familiar with. If you haven't studied anything beyond real numbers, you won't know what really that means. But we have talked about solutions of roots, which had no real solution. That's mean you get something where you got a square root of a negative number and you've got nothing that works in terms of a set of real numbers. So we'll come back to that concept. That's important if you study stage 2 specialist maths. But we will introduce in this assignment complex numbers later on. Okay, but for now, don't worry too much about that. Every real polynomial degree 4 can be factorized in one of 7 forms. I actually counted 8. In your investigation, we'll consider a number of the 7 forms. The aim of this project is to investigate the graphs of real polynomials of degree 4 with particular reference to the number of turning points and the number of inflection points. Now, we need to remind you of what these are. Okay, but let's start with the Now I count them as 8. Okay, so these are all the order 4 polynomials you could possibly graph. Actually, I'll rephrase that. Is this a sample of order 4 polynomials that you can graph with each example of how they interact with the x-axis. So, for example, you notice that all my polynomials here point up to positive infinity. So they're all values where a has to be positive. If I was to graph all of them that were negative, well, I'll double the list. There's also a lot more things that can interact. You notice that sometimes the bottom of the graph seem to line up together. They don't have to. Sometimes they kind of straighten out like this. They don't have to. There's actually a lot of freedom that can happen. If you go explore this in great detail, there are many other types of graphs, but I counted 8 ways that the graph can interact with the x-axis. And let me explain to you each of these. All right, so the number 1, you have 1, 2, 3, 4 linear factors. They cut, 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 cut 4 times. And you end up with this W shape. If A was negative, it would be more like a McDonald's sign. All right, the second one, you have 2 linear factors, so 2 cuts, and 1 quadratic factor. That's like 2 cuts and a touch. Now you can also, the value of gamma here, the touch, could be on the left-hand side, could be in the middle of 2 of them. There's a whole bunch of ways you could graph this as well, and you'll see that. Number 3, double touch. So you have touches at alpha, touches at beta. So alpha, beta, beta, alpha. It could be upside down. Not as much freedom as the previous example, but they're still infinitely many, because there's infinitely many values of A and alpha and beta. All right. Now, 4 through 6 is where you have at least 1 quadratic factor that cannot be reduced in the set of real numbers. So in other words, the discriminant, so you might notice that I'm not using the conventional a x squared plus bx plus c, because I'm using the a at the front. But if you consider that as a, b, and c, b squared minus 4ac is less than 0. So this cannot be reduced. There's no roots for this in real numbers. As such, so now I've got a quadratic factor. It touches at alpha and doesn't touch anywhere else. Number 5 is a special example where it can be reduced into 2 quadratic factors that have no real roots. This is the one you're probably going to ignore entirely for this investigation because it's not helpful. It's very hard to graph these without technology, because you've got no markers for what they're doing, which is unfortunate. So it's really hard to graph these unless you understand calculus very well and you can actually find the turning points algebraically. Otherwise, you would have to stick something like this into a graphics calculator or other emulator and graph that. So as far as the number 5, you might as well just cross that out, and then your 1 through 4 and 6, 7, 8 make up your 7 forms. All right. Now, number 6, we have 2 linear factors and an irreducible quadratic. So you see it cuts twice and then does it again. Now, there's no reason why this part has to be flat. It could come down a little bit and then just not quite reach the x-axis. It doesn't matter. It's that's just an artistic choice I decided to make for this one. Now, this one's very interesting. It is this is the basic version of quartic. I have put a coefficient. I have shifted it to the right. So you could graph something like this, where it just touches in a very wide kind of fashion and then branches out at alpha. Yeah, not much more to say about that. I'm just saying, but also when you look at number 5, I could, if I was to shift that up, so like add 2, this would be entirely positive definite, and it could actually make the criteria for number 5, which is why I say number 5 is probably the one you're not going to include in your investigation, because it's without technology, there's so many variants of that form, especially all the other ones just never touching the x-axis. Okay, and this last one. Okay, this one has solutions. It has a one where it cuts at alpha and it cuts horizontally at beta. This is the cubic factor does this behavior where it bends and flattens out. It does cut through beta and then it continues. Okay, so now that you kind of talked about the 7 forms, we're going to be looking at ones in great detail, particularly 1 and 2 initially, and then you have more freedom later on in the later parts of the assignment to explore a lot more of these, and also order 5 and so degree 5 and other types of polynomials that you might want to look into. Because in terms of polynomials, it's there's a lot of common behavior when you think about these factorized forms, and we'll see that in a minute. All right. So let's just have a look at part A. Investigate using, actually no, before we, no, let's just talk this through, and I'll also introduce these points while I go through, because I've got a little tool that will help with that. Investigate using an appropriate graphing package at least 3 real polynomials with 4 distinct linear factors in the form of px equals, the general form, basically like my number 1. What we're looking at. Present the information in a small graph for the table below. An example of the table that could use present below. Okay, yes, you can feel like that basically. Okay, all right. And in part 2, you're actually doing it with 5 distinct real factors. So that's order 5. All right. Now, one thing you can do with your textbook, you can go through this graphing package for this assignment. This is actually quite helpful. And it actually has a number. If you click on this little thing for investigating 3, it's a very similar investigation, at least for the order 4 polynomials. And you actually see they have a list of different polynomials. The first one is one such as this. So you can see you've got, okay, 4 linear factors, and you've got 4 x-intercepts, and you can investigate that. I'm not actually going to use this one, but I thought I might mention it because you've got a lot of different, you can actually go through all the different types and explore them. So it's worth taking this. By the way, you can also copy these and use them in different emulators. And I'll show you what I mean right now, because I'm actually going to jump over to Desmos, because I'm very familiar with Desmos, and a lot of cool things I know how to do on Desmos, and I'll use this to explain. I'm actually going to bring, no, not that. I want to bring the investigation. I'll bring that over this side. Okay, so I want to show you some. Now I've just made literally a generator for an order 4 polynomial with 4 distinct real roots. What I mean by distinct, alpha, beta, w, and phi cannot be equal. Now, unfortunately, I couldn't find gamma and the other variable, but delta. It doesn't like it. Like you can type in beta and it comes up with the beta symbol. I can't do that with the other ones. So it's gamma and phi. Okay, that's what I got. But notice here I've got, now this one I didn't actually. Okay, so I've actually got sliders for all the zeros, or all the roots of the polynomial. So I've got w, alpha, beta, phi. And I can actually move these around. I can change these. So see, watch that. Is that cool? Yeah, you can put them wherever you want. And that's what you're going to do, because you've got to do a few of these. So you can't just do 1 or 2. You have to at least do 3. At least 3. Okay. And you could make this negative. You can make it positive. My suggestion is, because you've got the choice of how to do it, you can use small integers. Small rationals, so like 1/20th. That just makes it fits nicely into like a square domain. So you can put it on your graphics calculator without having to play around with windows too much. So if it's like shoots up to very large values and you can't see much of it, you're welcome to just play around with A, because A is the most irrelevant thing in this investigation, as you discover. So for example, if I made that 2, well, this just makes it taller. It cuts through the same points. So I might as well just go back to 1 or 3. Type 3 in there. It doesn't matter. So, and you can make it negative. And what does it do? It just makes everything upside down. Boom. There you go, upside down. Upside down, upside down. Okay, but here's something very clever that I discovered, because I know how to do this stuff. Not so much. That's not what I wanted. Why is that not working? P. I've now stuffed that up. All right, it's not doing what I thought it was going to do. P. Oh boy. Okay. For some reason, oh, I see one. Okay, that's because I relabeled these because I was playing around. But there we go. Okay. Now, what this is in terms of mathematics is not important because it's actually something you learn in stage 2 methods or specialist. But basically, it's what it is it is a tangent function. It works out the tangent to the graph at any particular point of, in this case, P or X. But I'm using P as a placeholder. So you see I can move this and look what it does. It follows the slope of the graph as you move around. Isn't that cool? Okay. Now you say, oh, well, sir, you know how to do this, but what do I do? Graph it even on a screen and just hold up your ruler and just do something similar. You see when I'm swinging it around? You can just do that with a ruler. Okay. So let me explain what I mean by turning points. Now, you can find some turning points with the graphics calculator. There's one type that you can't, and I'll explain that in a minute. Okay, so the turning points are when the tangent to the slope are horizontal. So I'll show you what I mean. So I bring this around, slowly move it. Okay, about there. Maybe make it 8.2. There we go. Okay, you see how the blue line is horizontal? Well, what we found there, what we found in this spot, is a local maximum. Okay, so that's one turning point. All right, let's keep going. So, all right, get rid of that. And let's keep moving. Okay, we go down. There we go. Ooh, there's one there somewhere. Now, the value itself is not important. We're just counting how many there are. Okay, so that one has 2. All right, so we've got 2 so far. So that's the second one. And guess what? I think we're going to find another one up here. All right, 7.4 or 3.5, 3.6. Yeah, about there. Okay. So you got 1, 2, 3 turning points. That's what a turning point. A turning point is when the slope is horizontal. Okay. Say that again. So turning point is when the slope is horizontal. You might want to write that down. So you can go use your ruler, do all these graphs, you can find these turning points. What you should find is, particularly in this type, you will always find 3 turning points. There's the order 4 polynomial, 3 turning points. That might not be the case with the other parts, but for this one, you will find 3 turning points because it will always have this M or W shape. So there's always like 1, 2 local maximum in this case, 1 local minimum. Again, if I made that positive, well, guess what? You would find you'd find 2 local minimums and a maximum. So you've always got these 3 bumps to the graph in this respect anyway. Okay, with this set of graphs. We'll look at a different example in a minute. All right. So you have to do at least 3 of those and prove that you have 3 turning points. That should be what you find. Now, let me explain to you what an inflection point is. We've talked about how graphs can be concave, convex. I don't need to mess with that too much. Let's go back to my slide here. Okay, so you can see here, now you got the bit that's like this, that's the concave up, concave down, concave up. Basically what an inflection point is when the concavity changes. How can you spot that? Now, watch what I do with this. Now, I'm going to see if I can do this really nice and slowly. Don't need this much, just get rid of the, okay, let's get rid of that. Okay. So, if you move this around, so we just did that as a little animation. I'll play that again, and hopefully I wish I could play it a bit slower. Let's slow it right down. All right, so we're going to slow this right down. Now, when you have a look at how many times it changes the way it swings. So is it swinging clockwise? Is it swinging anti-clockwise? Let's have a look. So anti-clockwise, clockwise, and anti-clockwise. All right. There are two changes. Okay. So this is the part where it's convex. So here at 0, it is convex. All right. It changes here. So we swing out. The graph becomes very flat. Oh, sorry, not flat, straight. Doesn't necessarily have to be horizontal. That is one type of inflection. But in this case, it's very flat. Very straight. But you notice how the graph was swinging around. The right-hand side was going up. The left-hand side was going down. Now we get to here. That changes. It's no longer swinging anti-clockwise. It is swinging clockwise. The right-hand side is going down. The left-hand side is going up. But then you come to this point here where it swings back the other way. Okay. So what does that mean? There's an inflection somewhere around here, and there's an inflection somewhere around here. There are two inflections. All right? So number turning point 3, number inflections 2. Now, you have to prove this for yourself, but you can do that in that sort of respect. That's how you find them. Okay. Now, the next section is you're actually looking at okay, that's another type of graph, which I won't deal with right now. All right. So let's go, and I'm going to make up, you know what, I'm just going to add to this. Why not? I'm going to say x minus h. Oops, why I say x minus h. And come up with a little thing, add a slider for h. Yeah, sure, why not? And we'll do that. Okay. All right. So you notice here, now it's actually, I'm going to, okay, h is 1. Okay, let's make it, let's do something like that. Okay. Now it needs to have 3 linear factors. So I've got, 5 linear factors. This is now what we call an order 5 polynomial. I'm actually going to reduce this significantly. I'm going to make that 100. And then, oh, that's a bit too much. Let's make it 50. It's just that particular one's very out there. What's that one say? That's that one. Let's bring that one in. Okay. I want to make it nice so I can actually see most of it. Okay, so you can see most of it like this. All right. This is now an order 5 polynomial. So degree 5. I keep saying order. Degree 5 is the degree is what they call in your textbook. All right. Now, I've actually made that on top of what I had for my quartic. So this is now degree 5. But this tangent function will discover what's going on here. Now, so let's have a quick look. Count how many times it is horizontal. So let's have a look. I'm just going to do slow animation. So let's go do it. 1, 2, 3, and 4. Okay, 4 times that is horizontal. So we're actually looking at, which one we're doing? Now, actually, one thing I forgot to do actually was, you see there's a little bit of missing stuff in that. That's because this is in Google Docs and we actually need to download it properly, otherwise it won't work. So let's do that. So, okay. All right, so I'm actually going to bring okay, so let's actually look at this properly. There we go. Stop it. Computer struggling. There we go. All right. Oops. Stop it. What are you doing? Silly computer. Don't know why you're struggling so much. Not that much work. Oh yeah, here we go. So at least 3 times, yeah, 5 to 6, yeah, that looks a bit healthier, doesn't it? Okay, yeah, so it doesn't like certain like things. There's an issue with Word and Google Docs when it comes to particularly equations. So yeah, we're onto this part with 5 distinct real linear factors. Present the information. So when it came to 4 distinct linear factors, we had, so it was a degree 4 polynomial. It had, it has 4 distinct real roots, but you can write down which roots they are. It had 3 turning points and 2 inflections. Now, we've discovered for this particular example, 5 distinct real linear factors and degree 5 polynomial. It has 4 turning points. Let's have a look now. We'll play this animation again. I want you to count the number of times it changes its direction of swing. So it swings from anti-clockwise to clockwise or clockwise to anti-clockwise. Let's have a watch. Okay, sorry, it's still finishing the last animation. Start again. Swinging anti-clockwise, anti-clockwise, 1, 2, 3 changes. Okay, so that's 3 changes of concavity there. All right. So in that respect, order 5 polynomial, degree 5 polynomial, 4 turning points, 3 inflection points. Now, you should, when you make a conjecture, all you need to do at this point is make a logical guess about what you've seen so far. So make a statement in terms of this function and what you see in terms of turning points inflection. And you're also doing this in terms of polynomials of degree 4. So you do degree 4, you do degree 5. You can, if you want to, you can do degree 6 and so on with, follow this format so you have another bracket with a linear factor. Is there a relationship between the degree of the polynomial? Is there a relationship between the degree of the polynomial, the number of turning points, and number of inflection points if they are made up of a degree number of linear factors? Okay, so that's what you do for part A. I'll let you explore that for yourself. Now, I'm actually going to briefly, very briefly, I'm going to talk about another section. Okay, well, what if we get rid of that? And we're actually going to get rid of that as well. I'm actually going to square this one. Okay, so we've got degree 4 with 1 quadratic part. Okay, so it's actually that one there. Okay, so let's make that, we'll get rid of that. We'll make that a bit smaller, 20 will do. And let's make it also that, let's make it 5. There we go, that looks nice and healthy. All right, so we've got a nice W shape, but it touches, not cuts, at 2. So let's play our animation. Again, we're going to count. So we're looking at the first part of degree 3. All right, so let's play our animation. First of all, we'll count the number of turning points. So let's play this again. Let it finish first. Okay. Play our animation. 1, 2, 3. Okay. Play that through. Oh, that's a bit boring. Sorry, go through this. Skip ahead. Okay, skip ahead. Okay. Yeah. Now, so we had 3. So we have order 4, degree 4 polynomial, 3 turning points. Let's count the number of inflections. 1 turn, 2 turns. Okay. All right. So actually you get the same results as before. So do degree 4, 3 turning points, 2 inflection points. There seems to be a theme. So my conjecture would be maybe, and see for yourself with your examples, maybe in these 2 formats, degree is n, number of turning points is n minus 1, and in inflection points is n minus 2. However, I'm going to show you, we're going to come up with an example where that's not the case. So I'm going to make an example. I'm going to call this, because I'm going to have to make something up. So later on the assignment, you do have a bit more freedom as to what to pick. You don't have to pick particular types. You can go to any of the types. Let's go to order for polynomial, where I know that this is going to be a bit different. So let's get rid of that one. All right. So this is actually going to be, this is going to be my F2. Yeah, so I've renamed these polynomials. Okay. So I'm going to have I'm going to put a cubic. No, let's do let's do a cubic. Later on, you do have to do at least one with a irreducible root. But let's put a cubic in here. I didn't want to make a point of this. So we have that, and let's put past that, we'll put a linear. Okay, because that will make a, okay, there we go. All right, so that is a quartic as well, order degree 4 polynomial. And let's play a little animation. All right, so how many times is it horizontal and how many times does it bend? Okay, let's play our animation, see what happens. Okay, yeah. Okay, go back to start. Okay, 1 times horizontal, 2 times horizontal. Okay, actually order 4, and that one had only 2 turning points. That's what we call a stationary inflection, whereas is an inflection point and it's horizontal. We'll now go back and look at the number of times it bends backwards, bends the other way. We'll have a look at that. Okay, turns around one way, back around the other way, then back around the other way. Okay, so there is actually 2 inflection points still. That's consistent with order 4 polynomials so far. But there's only 3 turning points. I'm going to give you one more particularly interesting example, which would be, actually, why don't we just stick with this? I'm just going to change it. Let's just go with the most basic one. How many ones will you see here? Now, what's happening here is once we do these, once we get a lot of similar factorizations, they do reduce, because basically what's happening is, and I can show you by going back to the original graph, well, if these numbers all start to occur around the same place, well, everything gets compressed. So let's have a look at what happens with our animation this time. It's going to be kind of boring. So in this case, how many times does it flatten out? 1. Stop that. How many times does it turn one way, then turn the other way? 1. Oh, it doesn't really, no. It actually stops and then it doesn't really do it. So technically you can even say that's 0. Actually, I know that's 1, but because of things in calculus, I can't, we're not going to cover right now. So that's an interesting example. And if you go back to the original graph, if you start bringing these numbers together so they're not distinct real roots, sorry, I've gone and changed that, haven't I? That's why that one doesn't work. But if you start bringing these things together so they're like that, so yeah, we're getting that graph that we saw before. And if I was to bring, okay, that's 1.5, that's W0. If I bring that one, okay, that's that one actually. If I bring that one together, yeah, you're going to end up removing a lot of your detail when it comes to this stuff. So that's why in the early parts of the investigation, they'll tell you to do it a certain way, and you'll see some interesting patterns, and then you have a lot more freedom when it comes to the other parts. I'll cover in more detail later on, like what you actually have to do as far as writing the report. But at this point, do some graphs, write some tables, and have some fun. Okay. So it's been a bit long, but it's an introduction to this assignment. All right. So have a go for yourself. Catch you later.